Hello everyone, I'm Shaurya and today I will be giving you the problem solution of the problem 7 from the TCP Open Contest 1. Okay, so I hope you enjoyed the contest as well as the problem. So let's deep dive into it. The problem is the Great Raccoon Trash Chase. You can read the problem statement here. Let's read it together. Deep in the heart of Trashopolis, a city built on chaos and discarded leftovers, two raccoons ruled the streets: Drunkenstein, the mischievous trash bandit, and Rory, the obsessive cleaner. The city's allies and rooftops were all connected by one strict rule. Okay, they are all connected by one strict rule. Once a trash pile was pushed in one direction, it could never go back. Somewhere in web of pathways lay the final dumpster, a place where all trash inevitably ended up with no way forward. So basically it is indicating a acyclic nature, right? Acyclic nature. That once you move out of a node, you can never go back there, right? So a cycle is not present. Now, importantly, Trashopolis has one more rule. Once a trash pile moves forward, it can never return to an earlier ally. Again, the same acyclic nature that I was talking about. This ensures that every game eventually reaches a definite end, either at the final dumpster or when no further moves are possible. Right? One moonlit night, Drunkenstein challenged Rory to a game. He would push a heap of trash from one ally to another, while Rory would chase after it, ensuring it followed the natural flow of the city routes. The game would continue until one of them have no moves left. So when does the game end? The game ends when one of them have no moves in their hand, right? So the problem is trying to indicate towards a DAG, that is directed acyclic graph. If you will read the problem statement carefully, you will come to realize that it is justifying the properties of a drag. Properties of a DAG. That is, there are directed edges and the graph in itself is acyclic in nature. Okay, so the game rules are simple. What does the game rule say? Drunkenstein moves first. The first move is from Drunkenstein. He can push the trash to any connected ally where a path exists. Okay, he can push it to any directed edge. All right, any directed outgoing edge from that node. Rory moves next. She must let the trash roll along the natural path of the city following one-way street until it stops. Again, the same thing as above, in a different language. She can also push the trash to another position, that is an outgoing edge. The game alternate between them. The game is alternating in nature. The player who can no longer push the trash loses, so the other one wins, right? Now the challenge. The challenge is you, the great strategist of Trashopolis, have been given the city layout. So you are given the graph. Actually, your mission is to determine, given a starting ally, whether Drunkenstein can outmaneuver Rory or Rory will manage to clean up the mess efficiently. Both player plays optimally. Alright, both player will play optimally. You will be given Q queries. In each query, you must determine who will win if the game starts from the given alley. So in each query, you will be given a start index from where you have to start. Right? Let's see the input. The input format is simple. We are given n, the number of queries, the number of allies, m, the number of one-way paths, basically the directed edges. The next m line contains two integer li1, li2, representing one-way path from li1 to li2. Number of queries is q given. The next q line contains an integer, single integer s, that is the starting ally of that trash. The constraints are simple. N can go up to 1e4, that is number of allies or the number of cities can go up to 1e4. The number of roads are 1e5. We are given q queries, that can go up to 1e4, and in each query we are given a single integer, that is between 1 to 1e4. 1 to 1e4, right? 1 to 1e4, that is it will indicate to a city, right? Output format is simple. We have to, for each query, print D if Drunkenstein wins, R if Rory wins. Let's see a sample input. The sample input is simple. Here is the graph for the sample input. Let's see. Here this is nothing but N, this is nothing but M. This lines are M lines that indicate a graph. This is Q, and these are the Q queries, right? Queries, right? So let's see. Let me draw a graph once here, then I will explain the lower one. Uh, there are six nodes and 9 edges. So there is an edge from 1 to 3. All right. There's an edge from 1 to 3. There's an edge from 1 to 2. There's an edge from 3 to 2. There's an edge from 2 to 5. There's an edge from 3 to 4. There's an edge from 4 to 6. There's an edge from 5 to 6. There's an edge from 4 to 5. And then finally there's an edge from 2 to 4. Okay. And then there we have 4 queries. The first query is the starting index is 6. Right. So what if the starting index is 6 itself? If the starting index is 6 itself, then what will happen? Drunkenstein will win. Drunkenstein will lose, sorry. Why he will lose? Because he has no option. He cannot move it anywhere, and hence Rory will win. So for first query, the answer is Rory. Okay. Now in the second query, the start index is 4. What he can do from 4? Either he can move it to 6, or he can move it to 5, right? So if he moves it to 6, Rory will have no chance, because Rory cannot move it further. But if he moves it to 5, then Rory will move it here, and then Drunkenstein will have no chance. So because they are playing optimally, he will move it directly to 6, and hence Drunkenstein will win, right? So for the second query, Drunkenstein will win. Now for the third query. For the third query, the start index is nothing but 2, right? The start index is 2. Now from here, they can go. Drunkenstein can push it to 5 or 4. Wherever he will push, Rory will push it to 6, and then Drunkenstein will be left with no moves, and hence he will lose, and so Rory will win. And let's see the last one. The last one is starting index is 1. From 1, Drunkenstein can move it to 2, then 2 to 3, Rory will move, then 3 to 4, Drunkenstein will move, and then Rory will be left with no move, and hence Drunkenstein wins. And what if Rory moves from here to 5? Then again Drunkenstein can move it to 6, and again Rory will be left with no moves, and hence again Drunkenstein will win. So if they play optimally, Drunkenstein will win, right? So that was the sample input discussed. Now let's see the solution of it. You guys can clearly understand one thing, that the brute force will not work, right? The brute force will not work. Why the brute force will not work? Because we are given a graph of n vertices, and in each query we will need to determine need to determine who wins. We can do it using DFS or BFS, but it will take a big O of n time complexity. So the overall time complexity will be nothing but big O of q into n, and it can be approximated as big O of n square, which will give you TLE, right? So we have to come up with a better approach. Now let me show you the approach. But one thing is clear, the problem is based upon graph plus game theory, right? Graph plus game theory. But there's a bit more to it. You will see it later. So let me draw the graph again. It was something like this. Okay. There were edges from like this. 1, 2, 3, 4, 5, 6. 4, 5, 6. Right? Let's assume the start index is given as 6. Right? If the start index is given as 6, we have seen that Drunkenstein will be left with no moves. Hence, he will lose. We will play the game with the perspective of, with the POV of Drunkenstein. Right? We'll play the game with the POV of Drunkenstein, whether he will win or whether he will lose. Right? So here Drunkenstein will lose. So I'm indicating it with a L for lose. Right? Now let's see the next index. Next is 4. No, not 4. Wait. Let's see the next index as 5. You will understand why I chose 5. Now what happened if Drunkenstein plays from here? Then he can push Rory to a losing state. This state was a losing state, right? He can simply just push Rory to a losing state in the next move. And hence, this state becomes a winning state. Right? So, this state becomes a winning state. So, this is now a winning state. Now, let's check fourth one. Let's check this one, fourth one. Now, what do you see about the fourth one? That if Drunkenstein begins from here, he can push Rory to a losing state again, right? Here he can push Rory to a losing state again. If he pushes here, then what will happen? He will be pushing Rory to a winning state that we don't want, right? We want Rory to be in a losing state because we are playing optimally. So this also becomes a winning state. This also becomes a winning state. Now, let's see this one. From 2, whatever Drunkenstein moves, he pushes Rory to a winning state, right? He can move from to here or here. Both the states are winning state, right? So, whatever he does, he will push Rory to a winning state. And thus, this state becomes a losing state, right? So, hence, it is a losing state. Now, let's see the third one. Drunkenstein can push Rory to a losing state from here. Hence, this becomes a winning state. Okay, so this is now a winning state. Now, from here, he can simply push Rory to a losing state. So, this is also a winning state. So, I hope you got the idea right? What we are trying to do here. So the idea is, if we can push the opponent to a losing state, then current state will be a winning state, right? If we are able to push our opponent to a losing state, then current state will be a losing state. All right, what happened? And if we are not able to do so, we are not able to do so, then it is a losing state. What does that mean? Basically, if from the, let's say this is the current state, these are the states we can go to, right? If let's say this is a winning state, this is a winning state, this is a losing state, this is a winning state. So from here we can simply just move our opponent to a losing state, and hence this becomes a winning state. But if suppose this is our current state, this is a winning state, this is a winning state, this is a winning state, and there is no losing state. So from here, no matter where we move, we will give our opponent a winning state, and hence the opponent will, if they play optimally, will win the game, and hence this becomes a losing state. So the idea is very simple. If the adjacency of the current are all winning states, then then the current state is losing state. And if we found any state in the adjacency of the current state that is a losing state, then the current state becomes a winning state, because we can simply just push our opponent to a losing state, right? So that was the crux idea of the problem. Now how do we determine it, right? How do we determine it? I don't know if you understood or not, but there's one thing I did. I first checked the sixth one, then I checked the fifth one, then I checked the fourth one, then I checked the second one, then I checked the third one, and lastly I checked the sixth one. Let me write down this sequence, right? I checked 6, 1, 3, 2, 4, 5, 6, right? In this sequence I did. Now this sequence is nothing but a topological sort. In this you can observe that first I checked 6, there is no outgoing edges from 6. Then I checked 5, there is only one outgoing edge from 5 to 6, so 5 is before 6. Then I checked 4, 4 is before both 5 and 6, because 4 have outgoing edge to 5 and as well as 6, right? 4 has outgoing edge from 5 as well as 6, and hence 4 will be before that, right? Then I checked 2, 2 has outgoing edges from 2 to 4, 2 to 5, and then 5 to 6 eventually. Hence 2 will be before 2, 4, 5 and 6. Similarly 3 has outgoing edges to 2, 4, and then again 5 and 6. So 3 will be before 2, and 1 has outgoing edges to 3 and 2. So 1 will be again before 3 and 2, right? So this is nothing but a topological sort, and I moved from back of the topological sort. So the solution is simple. The solution is pretty simple. what we will do, first we will create a topological sort. Topological sort. Right, we will traverse from the back. Traverse from the back. Right, we will first mark all state as false, that is that they are a losing state. Right, and after that, after occurrence of each state, we will check the adjacency. Let's say we are here, we will check the adjacency of this, and if the adjacency of any of the adjacency of this contains a losing state, then it becomes a winning state. Right, and hence we will create a dp like this, and then we will answer each query based on this dp, each query based on this dp in big O of 1 time complexity. Hence by pre-computation of this dp, we will get a we can achieve a time complexity of big O of q. Right, that was earlier big O of q into n, and hence this is a linear time complexity and it will pass all the test cases. So let's see the solution. The solution is pretty simple. What I did first, I took n and m, then I created my adjacency vector and I took a in degree. Why I took a in degree, you will realize it later. Then I took my input u and v, I have taken, and I am taking it in a zero based indexing. Right, so I have taken the input in a zero based indexing. Then I have put from adjacency of u to pushback v. Right, and I have increased the in degree of v. If there is a edge from u to v, the in degree of v increases. Right, so in degree of v increases. Then what I did, then I am just debugging the adjacency vector and the in degree. So as you can see in this problem, the adjacency looks like this. This is 0 1 2 3 4 5. Right, the graph was, let me draw the graph here. The graph was looking like 0 1 2 3 4 5. All right, because it is in zero based indexing. Right, it is an edge from 2 to okay, sorry, there's an edge from 2 to 4, that is 1 to 4, this, and then there's an edge from 4. Let me see the graph once. Yeah, here, like this. We have an edge here and we have an edge here. Right, so you can see the adjacency of let me just erase it once. 0 1 2 3 4 5. Adjacency of 2 contains 2 and 1. Adjacency of 1 contains 4 and 3. Adjacency of 2 contains 1 and 3. Adjacency of 3 contains 5 and 4. Adjacency of 5 contains nothing. Right, because there is no outgoing edge from 5. And then in degree, again 0, the in degree of 0 is 0. The in degree of 1 is 2. In degree of 1 is 2. There is one edge here and there is one edge here. So it is 2. The in degree of 2 is 1. In degree of 2 is 1 from 0 to 2. And hence you can see the in degree here as well. Right. Now why I did this in degree thing? To apply Kahn's algorithm and have the topological sort. So here I am doing nothing but applying the Kahn's algorithm. This is a standard algorithm. I would suggest you guys to study about it. It is Kahn's algorithm. Right. I am taking a vector long topology as topological sort. I will suggest a video from Stiver of Kahn's algorithm, how BFS helps in taking topological sort in DAX. Right, you can just type it on the YouTube, Kahn's algorithm BFS Stiver. You will find this video. So you have to study about the Khan's algorithm. This is nothing but a standard code of Khan's algorithm. This is a standard code. There's nothing to explain over here. It is a separate topic. So after that, I got my topological sorting. So it is my topological sorting. You can see 0 is 0 comes before 2, 2 comes before 1, 1 comes before 3 and 4, 3 comes before 4 and 5, 4 comes before 5. So this is my topological sorting, right? Then in my topological sorting, now my step 2 is compute winning and losing states. I have reversed it. Why I have reversed it? Because I told you we will traverse from back, right? We are traversing from back, hence I reversed it here. Now current is my current state. Next is my adjacency of current state, if not of win of next. Matlab, if any state, like, sorry, how to explain this, like if there is no, the win of next is the state of adjacency of current, right? So if it is a losing state, then what happens? Our current state becomes a winning state, right? So in this, if we found here, if we have found a losing state, then our current state becomes a winning state, right? So if we have found a losing state, then our current state becomes a winning state. That is here. Like if we found a losing state, then our current state becomes a winning state, right? After that, I have debugged the win, and as you can see, the 0, 1, 2, 3, 4, 5, the fifth index is a losing state. This is a winning state. This is a winning state. Only the first index is a losing state, rest are winning state, right? And you can confirm it from here. Yeah, losing state, winning state, winning state, winning state, winning state, losing state, losing state. Only 2 and 6 are losing state, and here also only 1 and 5 are losing state. This is a 0 based indexing, right? So here it becomes 1 and 5 are losing state. So I hope the problem solution is clear. Now what we are doing in final step, we are taking the Q queries, taking the input start index, and this start index is in a 1 based indexing, so we are doing s-1 to get it into a 0 based indexing. And if it is a winning state for Drunkenstein, then we print D, because we have taken into account the Drunkenstein's POV, right? And if it is a losing state, then we print R. And in this way, we can do the problem in a linear time complexity. This was really a good problem. It contains all the logic of graph plus DP plus game theory, right? This problem might be rated somewhere around 1600 to 1700, let's say. And this was a good problem, really a good problem. You can find similar problems in USACO gold level, right, in the graph playlist. And you can practice more problems like this, and I hope you enjoyed the problem solution. And if there is any doubt, feel free to comment it in the comment section. Thank you.